Hello and welcome to our last lecture for ECE 108 for this week. In this lecture, we're going to introduce the basic ideas behind discrete probability, and don't worry, you will get lots of practice doing combinatorics problems for the rest of the term, so you get to keep honing your combinatorics skills. Okay, so we're going to introduce the fundamental idea of discrete probability by giving an example. Suppose I have a coin that when flipped has two outcomes, H or T. Now let's suppose that I flip the coin twice. If I flip the coin twice, my possible results are two heads, a heads and a tails and then a heads, or two tails. Now we might want to know how often we expect the combination of two heads to happen. This is what the study of discrete probability lets us do. It lets us quantify how often or how likely a certain event will happen out of a discrete set. So we're now going to introduce a bunch of definitions, so hopefully it's not overwhelming. So an experiment is something we conduct that has one or more outcomes. So for instance, flipping a coin would be an experiment, or flipping a coin twice would be an experiment. Thinking of the null set, that wouldn't be an experiment because there's nothing there. And the outcomes of those pre-mentioned experiments would be H or T for the first one, or HH, HT, TH, or TT for the second one. So putting it in slides, for example, flipping a coin twice would be an experiment, and the outcomes of that experiment we'll call elementary events. And elementary events are simply going to be elements of the set of all the possible outcomes. So in that case, if I flip a coin twice, these are all the possible outcomes. Elementary events will simply be subsets of that set. Now, the set S has a special name. The collection of all elementary events is called the sample space. So, sticking with the example of the experiment where I flip a coin twice, S would be the sample space for that experiment. Now, I can talk about things called events. So an event will simply be any subset of S. So for instance, HH would be an event, or HH with HT together would be an event. The sample space has a special name in terms of events. The sample space is going to be called a certain event. So we'll see later that we call S the certain event because its probability of happening is 1. It always happens. Likewise, the empty set has a special name. It's called the null event. It's the probability that nothing happens. So ultimately, after we formally define things a bit, the probability of the null event happening will be shown to be 0. So if I get two collections, A and B, we call them mutually exclusive if their intersection is the null set. So really, when I say that two events are mutually exclusive, I mean those two sets have nothing in common. And finally, the probability that an event E happens is the likelihood that E happens. So, a lot of terminology to kind of contend with there. Let's look at a couple of examples. What is the probability that a random integer from 1 to 100 is a multiple of 2 or 3? So here we're being asked what the likelihood of the event that a random integer or arbitrary integer that I pick between 1 and 100 is a multiple of 2 or 3. So to answer this, I need to know two things. How many ways can I pick an integer from 1 to 100? That's going to be my sample space. And how many ways can I pick a random integer from 1 to 100 such that it's a multiple of 2 or 3? That is going to be the event that I want to occur. So from lecture 23, we know that there's 67 integers between 1 and 100 that are multiples of 2 or 3. Okay, so there are 67 ways that this event can happen. Next, we know that there's a total of 99 integers between 1 and 100. So thus, if we pick a random integer uniformly, which we'll define in a couple lectures from now, from 1 to 100, the likelihood of picking a multiple of 2 or 3 is 67 divided by 99. So this example here is just showing the types of problems that we can address with probability and giving a little bit of motivation for the definitions that I gave before. And we will talk about this a lot more later. Okay, so in discrete probability, we have things called probability distributions. So a probability distribution, PR, is going to be a function from the power set of the sample space of S to the real numbers such that the following axioms hold. So explicitly, as a function, PR is going to take something from the power set of S and map it to some real number here. It turns out that the real numbers that it's going to map to are the numbers between 0 and 1 inclusive, but we don't formally need that in the definition here. Okay, so what are the axioms that we want to hold for that function to be a probability distribution? Well, we want the probability of event A happening to be greater than or equal to 0 for all events A in S. So for any given event, it has a non-negative probability. Next, I want the probability that S happens to be 1. So again, S is the sample space. We also called it the certain event. Why is it the certain event? Well, this axiom states that the probability that S happens is 1. Therefore, it is certain. Next, for mutually exclusive events A1 through AN, so events where each one of these sets have nothing in common, the probability of this union is simply equal to the sum of the probabilities of each of these events. So explicitly, what are these axioms really doing? Well, these first two axioms are setting up our probability distribution functions such that their range is between 0 and 1. And this third axiom here is giving probability distribution functions a forced structure that makes it useful for tackling problems. So again, since these are axioms, we can't prove them, we're just saying they're true. Or equivalently, we're taking these to be the three things that have to hold for any given function from the sample space of S to the real numbers to be a probability distribution function. So in the next lecture, we'll examine some important properties that directly follow from these axioms, namely claims 34 through 37. But for the rest of this lecture, we're just going to give examples of probability distribution functions and kind of give the big overview of why we care about them. Okay, find the probability distribution for the result of rolling 2d6. So what does the probability distribution for the result of rolling 2d6 tell me anyways? Well, it tells me the likelihood that certain numbers will show up on the dice. And oftentimes, if I'm, say, playing a board game or something like that, I care about, hey, what's the probability that I'm going to land on jail? Or what's the probability that the zombie's going to kill me? Wink, wink, homework problem. So in order to address these questions, I need to know what the probability distribution function is. Okay, so how do I do this? Well, first, I need to know what the sample space is. If I don't know what the sample space is, I can't possibly build a probability distribution function here. So what are the possible outcomes of rolling two six-sided die? Well, the list of all 36 possible dice combinations are here. So here, this is the result of rolling. So this is the result for the first die, and this down here is the result for the second die. So here, in this case, both of them are 1. Here I get a 1, 2, etc. So this is my sample space for rolling 2 die. So now I need to make an assumption about the dice to build a probability distribution. So explicitly, I need to assume that the dice are fair. That is to say, I need to assume that each one of these elements here is equally likely. So for instance, say if one of my die was weighted so that the number 3 pops up more often than the other numbers, then I get a different probability distribution function. So for this problem, I'm assuming the dice are fair, and if the dice are fair and each one of these events is equally likely, what is the probability of any of these given events? Well, there's 6 times 6 or 36 elements here, and the sample space S is the union of each one of these individual elements here, right? So from there, I can say that PR of S has to be equal to 1 because that's an axiom, but at the same time, PR of S is also equal to 36, because there's 36 options here, times the probability of, I'll just say E, where E is any of these events. It could be this one over here, it could be this one over here. It's just a single one of these outcomes. So this thing has to also be equal to 1. Therefore, from the second and third axioms of a probability distribution, explicitly this term here and the fact that the probability of S occurring is equal to 36 times the probability of E. And again, that comes from the facts that each of these dice are fair. From those two facts combined together, I get that the probability of any of these given events will simply be 1 over 36. So do note there are those assumptions built into them that the dice are fair, which makes these equally likely. So that's the probability that any of these events occur. So given this, how do I build the probability density function? Well, here I know that the probability distribution has to be a function from the power set of S to R. So that's pretty trivial setup to do. I want the probability of each of the events to be greater than or equal to 0. Well, here I've just claimed that it's 1 over 36, so that's true. I want the probability of the sum of all the events, or the union of all the events, to be equal to 1. That was true with the way that I constructed this 1 over 36. And finally, I have that third axiom that has to be true. Explicitly, I want the probability of, say, A union B to be equal, PR, to be equal to the probability of A plus the probability of B. So I want this to work for the union of arbitrarily finitely many sets, but it turns out that it's sufficient to show that it works for 2 sets, assuming we take induction as an axiom. So how can I build a function that satisfies this axiom here? Well, the simple way to do that would simply be to say that A gets mapped to the cardinality of A over 36. So now we need to show that this function PR, defined as follows, satisfies the axioms of a probability distribution function. So indeed, for any subset A of S, PR of A is going to be greater than or equal to 0, since for any subset of S, the cardinality will be greater than or equal to 0. Next, the probability that S occurs, well, S has 36 items in it, so the probability that S happens is 36 over 36, which is just 1, so that's trivially true. And then for axiom 3, why would that necessarily hold? Well, let's write out axiom 3 real quick. Well, axiom 3 would be that the probability of item A1 union ... up to AN, this thing would simply be equal to the sum of these probabilities. So PR of I from I is equal to 1 all the way up to N. So this would have to be true. Well, let's examine this function here to see what it does. Well, so this would have to be true given that A sub I are mutually exclusive events. So why would that have to be true for this proposed function here? Well, let's just plug it in by definition. So here, the probability of the union of these sets would simply be the cardinality of the union of the sets. So this would be P1 union ... of AN, all divided by 36. So that would be this left-hand side here is this. On the right-hand side, the sum of these probabilities, well, that's just going to be the sum of the cardinalities of the sum of these cardinalities, all divided by 36. So the question is, does this thing here equal this thing here? So big question mark. Well, yes, this is true. You can prove that this is true given that the sets are mutually exclusive. So to formally prove this with the things that you've been given, you really would want to use induction. Another possible proof would be to go back and use the method of inclusion-exclusion, abstract that so it holds for arbitrarily many sets. And from there, in the case where the sets are mutually exclusive, this the fact that this cardinality here is equal to the sum of this cardinality here, ignoring the 36s, comes out directly. Okay, so TLDR version from here. This is an example of a probability distribution function. But that's not the only probability distribution function I could potentially build based on experiments of rolling 2 die. For many board games, I don't care about what the individual dice rolls were, I care about what the sum was. So let's find the probability distribution for the sum of rolling 2d6. So for this case, I first need to talk about what the sample space is. So if I roll 2 6-sided die and then sum the pips, so the pips are the number of dots on the die, I'm going to get an integer between 2 and 12, right? And in particular, I can get any integer between 2 and 12. Thus, the sample space is simply going to be the collection of the integers 2, 3, up to 12. So now if I want to find the probability distribution function for these events, I need to know what is the likelihood that each event happens. Well, I can turn this likelihood problem into a combinatorics problem. How do I do this? Well, in order to determine the likelihood, I need to compute the number of solutions to x1 plus x2 is equal to n, where n is going to range between all of the values in my sample space. So explicitly, n can be any value between 2 and 12, and for my dice rolls, I know a d6 have sides ranging from 1 to 6, so this is what I want for my dice rolls. Now, we've talked about multiple techniques for counting the number of solutions to these types of equations under these types of constraints. So for this case, we can just do a brute force method. So the possible outcomes are, well, if I want to get a 2, I need to roll a 1 and a 1. If I want to get a 3, I need to roll a 1 or a 2, or a 2 or a 1, etc. Like if I want a 7, these are all the possible dice rolls that I can roll. So now if I want to build the probability distribution function, I want to know how often I will get a 2, a 3, a 12, etc. So I need to know the probability of each of these individual events under each one of these little boxes. So if our dice is fair, then each one of these rolls listed here is equally likely, and thus the probability distribution will be given by this function PR that takes an element of this set and maps it to R. So this probability function would be given by what? Well, if these things here are equally likely to happen, each one of these events has a probability of 1 over 36 of occurring. So for instance, 2 will have a 1 over 36 chance of happening because there's only one element, whereas 7 will have a 1, 2, 3, 4, 5, 6 out of 36 chance of happening because there's 6 events in its little bin. So from here, the probability distribution function would simply be given by this expression here. So these last couple of examples are just there as motivating examples for the various types of things we will be discussing over the next couple weeks during our discussion of discrete probability. So finally, just a comment on discrete versus non-discrete probability. So far, I've been using the title discrete probability, but what do I actually mean by this? Well, a probability distribution function is said to be discrete if it is defined over a sample space that is countable. So explicitly, when I say discrete probability, I'm meaning finite sets or countably infinite sets. For the rest of this course, we're going to focus on the case where things are finite, and we're probably not going to do anything with the case where it's countably infinite, but the majority of the results that we will discuss do work for countably infinite sets. The major distinction is when I'm talking about a function that is countably infinite, its cardinality is aleph naught. So some of the results where I say divide by the cardinality of the sample space don't make sense in that context. So let's give a few examples. Rolling a finite number of dice. that is going to be a discrete probability problem and a discrete counting problem. Flipping a countable number of coins, that will be a discrete probability problem. Randomly picking a card out of a deck of cards. So here I'm assuming a deck of cards is 52 cards. That is an example of a discrete problem. Pretty much anything that involves properties of people, age, vaccination status, etc. There are finitely many humans in the world. Therefore, we would use a discrete probability method when dealing with the set of all humans. That said, there are a lot of humans, and sometimes it's easier to work with non-discrete probability. Thus, oftentimes you will see non-discrete probability when working with problems involving the population of all humans. So now that we've covered some examples, let's look at some non-examples. Pick a random real number. This would be non-discrete. The sample space would be the set of all real numbers, and that is a non-countable set. Further, choosing a random n by n matrix and determining if it is invertible. This would be a non-discrete problem. So now, just one comment on the weirdness of non-discrete probability problems. If you were to choose a random real number, what is the probability that that real number that you picked is an integer? Well, there are integers in the real numbers, right? But it turns out that the probability of picking one of them at random is 0. So that's kind of odd. Next, if I were to ask you to pick a random 2 by 2 matrix, what's the probability that that matrix is invertible? Well, it turns out that the probability that that matrix is invertible is actually 1. So if you pick a random n by n matrix, it's essentially never going to be non-invertible. But on the other hand, we do know that non-invertible matrices exist, right? This is a bit odd, and to quantify why those facts are true, we need to talk about measure theory, which we're not going to do in this course. So here I just want you to keep in mind that when you start working with non-discrete probability, some of the fundamental assumptions that you would think would be true start to break down. Okay, so for your assigned reading, I want you to read pages 79 through 80. The main thing I want you to understand from these two sections are those definitions and the basic idea of what probability is, what probability distribution functions do, what those axioms are, and just the nomenclature that we'll start using for the rest of this course. Okay, so we have a meme. Teacher, if Tim enters a race with 4 other people, what's the probability of him winning? 50%. How is it 50%? He either wins or he loses. Listen here, you little. So yeah, this meme is an example where you're applying the wrong probability distribution function to your problem. And we will see an example of this in a few days when we talk about the Monty Hall problem. Okay, so that's it for this lecture. Have a wonderful weekend, and I will talk to you later.